So after understanding how to do equations of lines in space, let's talk about equations of planes in space. Is the point 413 on the plane 2x minus 3y plus 5z minus 11 equals 0? So, well, that should be easy enough to test, because if I asked you in 2 dimensions, is a certain point on a line, what do? You just plug the values of x and y into x and y in your equation and see if the equation's true. So we'll do the same thing here in 3 dimensions. So I'm going to put 4 in for x, and I'll put in 1 for y, and 3 for z. And if that's equal to 0, it'll be good. So we got 8 minus 3 plus 15 minus 11. And 8 minus 3 is 5, that's 20, that's 9. That definitely does not equal 0. So no, we know that that point, P, 413, is not on this plane. All right, so the equation of a plane takes on this general form. AX plus BY plus CZ plus D equals 0. Now, in some books or in IB, they're actually going to move that constant term D to the other side. So either way, it's still going to be the same equation. So in IB, they refer to this as the Cartesian equation of the plane. Now, there is one thing that's important, and we need to look at these coefficients here and this constant term D. First of all, we shouldn't have fractions or decimals. And so if you do have fractions or decimals, so if you have fractions, multiply by the least common denominator to cancel all those fractions. If you have decimals, multiply by the power of 10, that'll eliminate all the decimals. Also, A, B, C, and D should be relatively prime. And that means that they have no common factor. If there is a common factor, you should divide both sides of the equation by that common factor. So for example, if we had 2x minus 6y plus 10z, plus 4 equals 0, we could divide everything by 2, and so we get x minus 3y plus 5z, plus 2 equals 0. And that's the form we want to leave it in. So we don't want to leave it in that form with the leading coefficient of x as a common factor that we can factor out of everything. Okay, so let's figure out how we come up with the equation of a plane, and what do we need? Just like how did we come up with the equation of a line, and what did we need? Well, for a line we needed a point and a direction vector. All right, so for a plane, here's our setup. We've got a plane P, and we're going to let the vector v sub x, v sub y, v sub z, which is in blue, that's going to be a vector that's normal or perpendicular to the plane. Then we're going to let a specific point, x sub 0, y sub 0, z sub 0, be a point in the plane. And then the point xyz, the general point xyz, represents any and actually all the points that are in the plane. So with that setup, we can write the vector in green in the picture, x minus x sub 0, y minus y sub 0, z minus z sub 0. And it's important to understand that there actually will be numbers here. So you'll be, in a specific example, you'll be given a point in the plane, like 1, negative 7, 4, for example. And so those will be values, but the x, the y, and the z are variables. Just like you have y equals mx plus b. The m and the b are actual numbers, but the y and the x are your variables. Okay, so we have that green vector as any vector in the plane. And then we have the blue vector, which is perpendicular to the plane. So from what we know about vectors that are perpendicular, we know that the blue vector and the green vector, if I do their dot product, it should equal 0 because they're perpendicular. So that's going to be how I'm going to generate the equation. So if I take the blue vector, it's off the screen here, there it is. And let's do this in red, I guess. So if I do the dot product of my normal vector, v sub x, v sub y, v sub z, dot with this green vector, which is a vector in the plane, any vector in the plane that goes through the point x sub 0, y sub 0, z sub 0. So x minus x sub 0, y minus y sub 0, z minus z sub 0. That dot product should equal 0 because these are perpendicular. So that's what we need, is we need a vector perpendicular to the plane so we can use this dot product property that if they're perpendicular it equals 0. All right, so now let's go ahead and do the dot product. Well, we multiply the respective components and add the results. So I'm going to have v sub x times x minus x sub 0. So if I distribute, I'll have v sub x times x minus v sub x times x sub 0. And then I'm going to add to that, I should maybe circle these. There we go. So I multiplied the x components together and I distributed. Now I'll do the same thing with the y components. And so I'm going to get v sub y times y minus v sub y times y sub 0 plus, and it's important to remember and understand what each of these variables represents. So multiply that. So now I'm going to have v sub z. So v sub z, remember, that's the z component of your normal vector, times z, which is the z coordinate of any point in the plane, and then minus v sub z, that z component of our normal vector, times z sub 0, which is the z coordinate of a specific point in the plane, equals 0. Now let's regroup this a little bit. So I have v sub x times x plus v sub y times y plus v sub z times z, and then actually I can say minus all this other stuff if I factor out a negative 1, v sub x times x sub 0 plus v sub y times y sub 0 plus v sub z times z sub 0, and all that equals 0. So once again, as a reminder, v sub x, that's a specific number that you'll have in a particular problem. That's the x component of your normal vector. So we'll have a number for v sub x and v sub y and v sub z. The x sub 0, y sub 0, and z sub 0, those are the coordinates of a specific point in the plane. So we're going to have numbers for all of these. And so I'll add those all together, and I'm just going to get a value. I'll get a real number. So what I'd like to do, move that back over there, is I want you to think of all of this stuff as just a constant, and we'll call that d. And if you like, depending on which form you're using, you can move that to the other side, or you can leave it as is. So for IB, the Cartesian coordinate of that, so the v sub x I'm just going to refer to as a, and the v sub y is b, and the v sub z is c. And we'll have specific numbers for a, b, and c in a particular problem, equals d, and d is all that other stuff in parentheses. And so there is your equation of the plane. This is the Cartesian form. For the equation of a plane. Okay, so now let's put that to use. So now that you understand where the coefficients of x and y and z come from in the equation of a plane, the a and the b and the c represent the components of the normal vector to our plane, which was this blue vector up here. So if we can have a vector that's normal to a plane, we're going to use those components, and those are the coefficients of x, y, and z in the equation of our plane. All right, let's look at two examples. Find the equation of the plane that's normal to the vector 2, 3, 4, and it contains the point -1, 0, 5. So just to help make sure you have a visual for this, we've got a plane, we've got a point in the plane, which is -1, 0, 5. And then we've got a vector that's normal to the plane, which means it's perpendicular to any vector in the plane. And this is the vector, I'll write it this sideways here, 2, 3, 4. Okay, so right off the bat, I know my answer is going to look like this. AX plus BY plus CZ equals D. And I know that the A and the B and the C come from my normal vector, the components of my normal vector. So I'm going to have 2x plus 3y plus 4z equals some constant. And now I have to figure out that constant. Well, what I don't want to do is I don't want to go back and have you try and memorize this calculation here for that d value. I mean, you can if you like, but it's not worth it because there's a much simpler way to do this. And that's by simply taking this point, and we know that the point is on the plane, so it should satisfy this equation. So if I plug in 1 for the x, 0 for the y, and 5 for the z, I'll be able to figure out what that constant d is. So when I do that, I'm going to get 2 times -1 plus 3 times 0 plus 4 times 5, and that'll equal my constant d. So it's -2 plus 0 plus 20, so d is equal to 18. So therefore, the final answer, the equation of my plane, is going to be 2x plus 3y plus 4z equals 18. And it's easy as that. So as long as you have those two important pieces of information, just like if you have the slope and a point in 2 dimensions, you can get the equation of the line. So if we have the normal vector and a point, we can get the equation of the plane. Let's look at one more example. Just like we did with 2 dimensions, we can do some variations on that. And you'll be given enough information to come up with what we need. So to get the equation of the plane, what do we need? We need a normal vector to the plane, a perpendicular vector to the plane, and we need a point in the plane. All right, so what are they giving us here? They're giving us 3 points in the plane. So we definitely have satisfied point in the plane. We have our choice here. We could use any one of those. Doesn't matter. I'll probably use P. But then the next part is we need a perpendicular vector to the plane. Well, we have to go back to our bag of tricks and say, what do we know? Well, if we have 3 points, I could actually come up with some vectors using those points. I could get the vector PQ and PR, or if you like, you could do QP and QR, or RP and RQ. Doesn't matter, start from the same point though. And so let's find those. So let's do, I'll tell you, we'll do it in blank. Let's find vector PQ, and that's going to be terminal minus initial. So I'm looking at my coordinates for P and Q. So -1 minus 1 is -2, 0 minus 2 is -2, 4 minus 3 is 1. So there's PQ. Now let's find vector PR. Where are we going with this? I don't know. Not sure what to do? Do something. So let's find PR. So look at your coordinates for P and R, terminal minus initial. 2 minus 1 is 1. -1 minus 2 is -3. And 5 minus 3 is 2. All right, so now what do we know? What can we do with those 2 vectors? Well, what do we need? Let's go back to what we need. We need a vector that's perpendicular to the plane. So we need a vector that's perpendicular to both of those vectors that are in the plane. Well, if you remember back, we had an operation called cross product, and when you do the cross product of two vectors in 3 dimensions, you get a vector that's perpendicular to both of those vectors, and therefore perpendicular to the plane that they determine. So I'm going to do the cross product of PQ and PR, and that'll give me my perpendicular vector. Call it B. All right, so let's do our calculation for cross product. And I do that vertically, so -2, -2, 1. We're going to cross that with 1, -3, 2. And this is going to give me, I should have done this in blue, I guess. This will give me that vector V. All right, so our cross product is going to be, switch to blue. All right, so we hide the x. Let me show you how I'm doing this. It's hard to do it without you seeing the visual. There we go. So I'll hide the x components, and then I'm going to do -2 times 2 minus 1 times -3. So that's going to be -4 minus a -3. So -4 plus 3, which is -1. Then I'm going to hide the y components and do the same idea. And so I'm going to do -2 times 2 is -4 minus 1 times 1. -4 minus 1 is -5. And then for the y component, we take the opposite of that, so it's +5. And then we hide the z components and do this same idea. So we're going to do -2 times -3, that's 6, minus -2 times 1 is -2. So we get 6 minus a -2, so that's 6 plus 2, which is 8. So there's my vector V perpendicular to the plane. So now I've got everything that I need. I need a perpendicular vector. I got that. And I need a point. I have a plethora of points. Just pick one of them. I'll pick that one. All right, so this -158, those are the coefficients of x, y, z in the equation of my plane. So it's going to be, let's write it over here on this side. How about -1x plus 5y plus 8z equals d. And then I'll plug in the point 1, 2, 3 for x, y, and z. Doesn't matter which point you plug in. You'll get the same value for d. All right, now we simplify that. We get 10 and 24. We get 34 minus 1 is 33. So d is equal to 33. So final answer, the equation of the plane, it's going to be -x plus 5y plus 8z equals 33. And we usually like the leading coefficient to be positive. So you'll probably see this, as most answers would write it, as x minus 5y minus 8z equals -33. Now what we can do is we can double check and make sure, well, we know the point 1, 2, 3 works in there. Let's check this point Q. If I plug in those numbers for x, y, and z, I'm going to get -1 minus 0 minus 32, that gives you -33. So Q does work in that equation. Now let's try R. Put in 2 for x, we're going to get 2 plus 5 is 7, minus 40 is -33. So all 3 points work. So this is our equation, and we're done. Okay.